Hey there, ladies and gentlemen, boys and girls. Today we're going to do a little video talking about biology, but more focusing today on geology, study the Earth and Earth events and formations. All right. So we're going to talk about relative age dating today. All right. So we're still talking about the theory of evolution, but now we're going to start shifting a little bit towards what is the evidence for this theory. Now remember, the theory of evolution is a theory. It's an idea of what happens supported by evidence. The more evidence a theory has, the stronger it is. And so one of the biggest and first pieces of evidence that supported Darwin's theory of evolution, besides what he could see today, all right, so is the fossil record. All right. Now, remember, according to his theory, that evolution has been happening for a very, 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 very long time. And so the idea we should see evolution occurring not just today, the results of it, but we should see evidence of it occurring in the past. And so this is where we start bringing in some geological events. Now, remember, when we talked about Darwin and friends, is the idea that Darwin was influenced by Charles Lyell, who was a geologist. He was kind of a pioneer in the field of geology because he basically said that the Earth is very, very, very old, and all changes take very, very, very long periods of time. Excuse me. And so we're going to talk about the most basic way that we can use fossil records and geology and our concepts of geology to point towards supporting the theory of evolution. Remember, theory can't be proven by one thing. It's got to be an amalgamation, a combination of different evidences that makes it stronger. All right, so this is the first one we're going to do. We're going to talk a little bit about kind of the easiest one because today it feels a little obvious. But remember, things have changed. We're much more exposed to information these days. The first one we're going to talk about is what we call relative age dating. Which is basically trying to guess the age of specific fossils relative to everything else in relationship, not exact numbers, just like a first, second, third. All right. I did pretty well in the race. I ran a mile and I got second place in the race. Relatively, that's good. But if I would have told you that I got second place, but my time was 6 hours, right? Well, okay. Well, now you're saying, well, that's not a good hour or a mile run is 6 hours because relative second, I did pretty good. But when you get to actual specific numbers, that can be a little bit more, give you a better idea of what's happening. So, all right, first things first, is this something called in geology called the Wall Superposition. Basically, it says that the Earth is made of layers, right? These layers are called strata. That's an A at the end. Sorry, I ran off the screen there. These layers are called strata. These different strata go in layers by age, where lowest or the deepest ones from the surface. So here's our surface, right? Here's our surface. The oldest ones are at the bottom, and the newest ones are on top. Think of it like layers of a cake. If you're going to make a cake, you make the cake, you start with the bottom, and then you stack on top of it, and then you stack on top of it, and you stack on top of it, right? And so you keep building layers and layers and layers on top of each other. So now when we find fossils, all right, we find them in different layers, and we can kind of put them in order and just by relative say who is older. All right. So for example, here, all right, we have 4 fossils here, or in layers 1, 2, 3, 4. We have fossils A, B, C, D. The question is, which one do you think is the oldest? The answer is D is the oldest because it is in the lowest or the oldest strata, the lowest layer. All right. So this is the oldest, and this would be the youngest. All right. So once we put a collection of fossils together, we can start to kind of almost put a story together. All right. And that's the whole idea of relative aging is we could start putting a little, and I'll show an example. All right. Before I switch and talk about this example, though, I want to point out, all right, fossils are very hard to come by when you think about it. We found lots of them, but the process of creating a fossilization, takes very specific criteria. The organism has to die. It has to not be radically damaged or scattered. It needs to quickly be covered by something, by rock layers, where the carbon inside the bones is replaced by minerals in the soil or ocean floor or wherever it is. So it's a little bit tricky to be able to fossilize something. So a lot of people, it's hard to find these things. All right, so now let's use an example. And a very common example when we talk about this stuff is actually the fossil ancestors of whales. All right. Whales, we now believe, actually, their ancestors started on land. All right. And we tell that by putting kind of the story together of what we see in a specific area. All right. So what we might find is kind of this progression of fossils. Now, again, evolution is occurring at a very, very slow rate. It is not just one turns automatically into a new species and then radically into a new one. It is a very, very slow, gradual process over millions of years. Right? From year to year, from decade to decade, century to century, you would not notice the difference. But when you step back and now we look at over the last 100,000 years, right? Or over the last 50 million years, even, we can see the radical changes. So for in this example here, we have found in, say, a specific area that we believe that used to be, had lots of life. We might find, this fossil here in this layer, and we might find this fossil timed a little bit here, and this one here in the limestone, and this one here maybe at the top of the limestone, which means it's a little bit closer related. And then we would find, maybe in the shale, and then what we would consider the modern day whale placed at kind of at the higher levels here. And we could start to put a story together. Well, okay, in this region, right? If we kind of go backwards in time, here's a modern day whale, and this is what it looks like. But we have over time, we have this progression to, this is today. We have this progression backwards. It's almost thinking backwards in time. That, well, hey, here's this one that looks kind of similar to it, but these ones got a little bit longer bones, and it's not as long, but it's got longer arm bones, and it's got longer leg bones. It's very similar. Maybe this one over time turned into the modern day whale. And then you can keep going back even further. Well, there's that one. But then if we keep digging a little bit deeper, we find this one's a little bit like it, but notice the legs are a little bit longer. Maybe this one was not only in water, but also on land, maybe kind of both. And then we get a little bit further and we see, well, this one was clearly, it's still very similar. It's got the long tail, the elongated mouth, but it's just slow changes as we go through, and we start to connect them. Maybe they're all related, and then we get almost like this. You can see here on the left here, almost this cladogram where, they broke off right here, Here's a node. We have this species here, and then we developed into a new one here. And then we have another node that breaks off into that species and goes a little bit further. So on and so forth, where new species are being changed because of micro and macro evolution. All right. So the whole idea is that because of where we find them in the different these fossils in the different layer strata, we can kind of put a story together about how this organism has changed species over time due to micro and macro evolution. All right. Well, that's it. That's pretty much the concept of relative age dating, is that using some concepts like the law of superposition in geology, we can start to kind of say well, hey, look, species change. I start digging, I find whale bones. I dig a little bit deeper. I find what look like whale bones, but slightly different. And I dig a little bit deeper. These look like the other ones, but maybe just a little bit different in this gradual change over time. So that's pretty much it for relative age dating. Now, absolute age dating, which is a little bit more specific, telling me exactly how old those fossils are, is a little bit trickier. So you're going to have to do some background knowledge on what is half-life and radioactive half-life. on that one. That one's a little bit trickier where we can actually give a specific age of those fossils. But that's it for relative age dating. If you have any questions, make sure you go back. Make sure you copy down some of the things, the notes that you thought were valuable or important. Otherwise, thanks for watching and good luck. And may the science be with you.